Hello, everyone. This is Ujjwal Gandhi from SpatialThoughts.com. I want to welcome you to this module on reducers. This module is part of our advanced course on Google Earth Engine. In this module, we do a deep dive on reducers and learn how you can use them to build complex workflows. All the course materials, including the presentation and the code repository, are linked from the video description. What follows is the recording of an instructor-led session where I taught this module, and we are making it available for free to everyone to learn and use. So enjoy. Let's start with this module on reducers. In this module, we'll start with an overview of reducers, what they are, why are they used, how you might understand them, etc. Then we'll cover different types of reducers. We'll cover combined reducers, repeated reducers, group reducers, weighted versus unweighted reducers. Most of you may not even be familiar with any of these terms. Some of you might have heard of it. We'll try to do a deep dive and understand what each of these terms mean and how this reducer is useful. Once we cover this, we have some advanced use cases of computing zonal statistics. We'll see how you can do this by combining everything we learned in the class. Let's start with the overview of reducers. So what is a reducer? All of you would have used reducers in Earth Engine. Probably the very first day you used Earth Engine, you would have used a reducer, right? You have loaded some image collections and you would have said median, right? That's a reducer. Reducers are used for computing statistics. So when you create a median composite, you are taking multiple images, multiple pixel values, and computing a statistic. Reducers are also used for performing aggregations. So you take multiple values, you compute a histogram, right? So that's a reducer operation. In Earth Engine, reducers are used widely. Whenever you want to aggregate data, so you have image collection and you want to create a composite, you use this. If you have multiple bands and you want to create a single band out of it, you use this, right? So across all kind of data types, whenever you have multiple values across space-time and you want to aggregate, this is where reducers are used. Reducers are objects which are able to perform this aggregation. There are two broad categories of reducers in Earth Engine. There are simple reducers for computing statistics. So things like e-reducer mean, median, min, max, right? So these are something that you give it values and it'll compute a statistics on that. If you give it a stack of images and say, I want to reduce it using the e-reducer median, it's going to compute a pixel-wise statistic and give you that value per pixel. Right? There are other categories of reducers which are doing more complex summarization. So things like e-reducer histogram. You give it all the pixels in an image and it'll give you the count of pixels per bin, per category. Right? So you can compute that. That's also a reducer. There are reducers that can do linear regression. So this reducer will give you the best fit line between the X and Y values. Reducers are also used for computing correlations and things like that, right? So again, two broad kind of categories. These are the reducer objects, and there are hundreds of those available under the ee.reducer module. If you look at your docs and open the ee.reducer, there are all these reducers that are available to you to compute different kind of statistics. So we know about these reducers. How do we use them? Well, as we learned, we can apply it on many different kind of objects. If you take an image collection and you would have run this function, right, dot median, and this will create a median composite per pixel from all the pixels in the image, all the images in the stack, and this will aggregate the images temporally. And there are a few shorthand functions like this: median, mean, max, etc. They are shorthand for a more generic function called dot reduce. So if you have any image collection, you can say dot reduce and give any of the reducers, and it'll run that statistics. So dot median is equivalent to saying dot reduce e-reducer median. Okay, they both are identical. The second syntax allows you to run any reducer versus the first syntax. There are only like 10 shorthands available for the most commonly used ones. But if you want to run, say, create a 25 percentile composite, there is an e-reducer percentile, but there is no dot percentile, right? So if you want to do that, you will have to use the full syntax. So this is kind of the most commonly used reducer operation, where you take a collection and you call dot reduce on that. You might have also used a reducer on an image where you would have said reduce region, where you give a geometry and say, give me the statistics of all the pixels within that. give me the average value of all the pixels in this region. Right? That's a reduce region function. There's also reduce regions, plural, where you give it a feature collection. You have multiple polygons, and it's like, give me the average value for each pixels within each polygon. Right? And each of these functions will ask you to specify a reducer object, which we learned in the previous slide. Okay, so these are kind of the most commonly used ones. But in Earth Engine, almost all of your image processing and remote sensing operations are implemented as reducers. So as you start implementing your remote sensing workflows, you'll discover that there are reducer functions available for many other objects. So for example, you can reduce an image. So if you have a 10-band image and you say reduce, you will get 1-band image, run across all bands. There's a function reduce to vectors. You have an image and you want to convert it to vector. You want to create polygons from contiguous pixels. Each of this function will ask you to specify a reducer, and you can choose which reducer makes sense for that particular application. There's reduce connected components, which say I have, when you want to do some object-based analysis, you find a group of pixels and say, for each group of pixels, I want to compute some statistics. Reduce neighborhood. All the kernel operations are implemented in Earth Engine as reduce neighborhood function. Reduce resolution. This is an aggregation function. You have low resolution raster. You want to aggregate it to lower resolution. So you want to match Landsat and MODIS. You will aggregate Landsat to MODIS resolution. Or you have a population data and you want to aggregate it to climate pixel size, right? So when you want to kind of match pixel sizes and aggregate, this is the function that you use. For feature collections, if you have tables, vector data in Earth Engine, you can also run some reducer functions. There's a reduce to image, which will convert a vector to raster, opposite of reduce to vectors. On feature collection, there's also dot aggregate functions. So things like aggregate mean, aggregate max. This will allow you to take all the properties of a feature collection and run some statistics. So let's say you have uploaded a shapefile and you have an attribute, and you say, I want the average value of the column. There'll be aggregate mean of that property. There's a generic function called reduce columns, where you can compute statistics for multiple columns. So again, same thing as the first one, but you can do the second one for multiple columns. Similarly, if you have an image collection, you have multiple properties, and you can say reduce columns for images. So let's say you have a metadata cloud cover for each image, and you want to say, what is the average cloud cover for all images, right? You can use this reduce columns on an image collection. And of course, you can run reducers on list and arrays. These are, again, you have multiple items in a list. You can run that by calling the dot reduce, and similar for array. So this is, again, for your reference, just to help you understand where all reducers are used. And you can see many, many operations, from kernel operations to vector to raster conversion to aggregation. Everywhere you need to use reducers. One of the things that you need to think about now, since you are now learning advanced Earth Engine, is about reducer inputs and outputs. Each reducer object will take one or more inputs and will generate one or more output. Yeah. So, and how many inputs and how many outputs will depend on type of reducer. Let's take example of this reducer. This is a reducer, EE reducer mean. So average, it'll compute average. It has got one input and it'll generate one output. Now, when we say one input for a reducer, that's not really one input, right? It's a one series of input. So you give one series of values and it'll generate one output value. So you give a series of values 2, 3, 4, 5, 6. The reducer will compute average of those. Okay. Simple to understand. There are other reducers which might take one input, can generate multiple outputs. So look at this reducer, EE reducer min max. This is going to generate two outputs, right? Min and max. There are other reducers which will take more than one input. So for example, this reducer, EE reducer linear fit, takes two input series, a series X and a series Y, and it'll generate the best fit line to this. So it'll generate two outputs, slope and offset. Okay, so each reducer have multiple inputs and multiple outputs. And this is very important when you start using more advanced reducers. You need to keep in mind what are the different inputs needed for each reducer and how many outputs it generates. So now let's understand different types of reducers. The first one we're going to cover is something called a combined reducer. So far, you might have used one reducer, right? E-reducer median, E-reducer mean. Let's say you want to compute multiple statistics from the same data. You can actually run the same reducer twice. So you can say reduce region for this region mean, and then take the same image and say reduce region standard deviation. Right? So you can compute mean first and then standard deviation. Now, if you do that, you'll be running the computation twice. That means you'll be reading the pixel values, computing the statistics. Again, in the next step, you'll be reading the same image again, computing the statistics. Instead, you can just say, read this image and compute multiple statistics together. And this will run in parallel. Since you're already reading the image, you have the pixel values, you can compute multiple statistics. Many applications will require to say, compute many different values. Mean and statistics is one example. Mean and standard deviation is one example. So if you want to compute both, just create a combined reducer. The function is called combine, where you have a reducer object and you say combine the second reducer. So you take first reducer dot combine and the second reducer. When the combine function has one parameter called shared inputs. This is a parameter will say you are combining two reducers. Do they run on the same inputs or do they have their own inputs? So remember, reducers have inputs. Let's say each reducer has one input and you combine them. Do they run on the same input or do you want to give them two separate inputs for them? Right? This is what the parameter says. If you say shared input is true, they'll all run on the same input. If you say it's false, they'll run on separate inputs. Let's say visually how this works. We have an input series with some values. We have one reducer. Let's say we want to combine it. We'll say combine a standard deviation reducer. And when we combine, we'll say shared input is true. That means you'll get two outputs, mean and standard deviation of the same image, same series. If we did this, we had two inputs. Let's say we have two series. We combined two reducers and we say shared input is false. That means each input gets its own, each reducer gets its own input. So here you will get mean of input one and standard deviation of input two. Okay, so each reducer, when you combine, they get their own inputs if they have the shared inputs. So this is not very commonly used. With the more commonly used one is where you say, I have one input, I want to compute multiple statistics. So combine reducer with the shared inputs. All right, let's do a coding example showing the combined reducer. So we'll start with an example of the reducer with code. In this repository, we have the reducer section here. We have all the code available here. We'll start with the script 1A. I'll build the full script and the full code is already available in script 1B. Okay? So this is an example of combined reducer, which we just learned about. Let me explain the setup here. We are using MODIS imagery. This is MODIS vegetation indices. This is an image collection where each image is a 16-day composite image with NDVI and EVI, two bands. For this example, we are just selecting the NDVI band. So we have NDVI at every 16 days, and we just computed the mean NDVI over 1 year. Okay? And this is an image. So you have an image, which is the average NDVI at each pixel for 1 year, and you have a geometry, right? This is the region. Now let's compute some statistics, and we'll see how we can use combined reducer here. The first one we want to compute is, let's say, what is the average NDVI in the region? Okay. So let's say, take our image and we'll run this function, reduce region. Control space to autocomplete. We'll also autocomplete all the parameters. So this is a function that will compute statistics for a region from all the image pixels. It's asking us for a reducer. Let's give EE reducer mean. Geometry is this geometry variable. Scale, we are using MODIS. The resolution is 250 meters. We'll skip the CRS, etc. Let's just use this. Let's print the result. The result of a reduced region is always a dictionary where you get one value per band. So if you had 2 bands, you'll get 2 values. Okay? But here we had 1 band and we got 1 output. So we had 1 reducer, E reducer mean, with 1 input, right? 1 series of input, which is all the pixel values of NDVI within this region. The reducer took those values and generated 1 output, which is the average value of those pixels. Okay? This is a dictionary. So if I just want to print this, I'll just say get number and NDVI. The key of the dictionary will be the name of the band. So in this image, the band name is NDVI, so that the key was NDVI. And so we could compute this average NDVI within this region. Simple enough. But now let's use a combined reducer. Let's say I want to compute both mean and standard deviation. Okay. So I'll take this code that we wrote previously. And now we have this reducer object. We'll say, I don't want to use a single reducer. I want to use a combined reducer. So we use this function combine. And these are the parameters. So I'll say, what is the reducer to? What's the second reducer you want to combine? We'll just say reducer standard deviation. Output prefix, you can change what the output prefix will be. Typically, it'd be whatever is specified per reducer. It'll be mean for mean reducer, STD, EV for standard deviation, and so on. So we'll just keep it default. Here is our shared input parameter, right? Here we have 1 input, right? 1 series of input from this 1 band. We want to compute statistics from the same pixels. So we'll just say shared input is true. Rest, everything remains the same. Let's print. And you can see the difference. Now we got both mean and standard deviation in the same operation. So this is highly efficient. If you just had repeated the same thing with a different reducer, you would have got those numbers, but it would have taken twice as amount of time. So if you want to compute multiple stats, always use a combined reducer, which will allow you to compute the stats in one go. And we can keep going, right? So let's say we want to compute more statistics. Let's combine some more reducers. You can also create those reducers first and then use them. So let's just say I want to create a variable called all reducers. I'll take my E reducer mean and I'll say dot combine, and we'll say E reducer standard deviation, or let's say I want to do min max, and we'll say shared inputs true. So this is a reducer where it'll take mean and min max, and it'll create a combined object. And now I'm going to use this one. So we'll copy this code. And now instead of writing all the code here, we'll specify so now we'll get the same statistic, but now we'll get mean, min, and max, right? We got 3 outputs. Let's add some more reducers. So one very useful reducer is this E reducer percentile. Median value is the 50th percentile value. And this is useful, but sometimes you want to get interquartile range. So 25th percentile and 75th percentile. So this E reducer percentile will allow you to do this. It takes a list of what percentiles you want to generate. So if you just specify this, it'll say, I want the 25th percentiles value. So now we'll get average, 25th percentile, min, and max, all of them together. And this reducer takes a list. So I can also say, give me the 50th percentile, 70th percentile, and so on, right? I can give all the percentile values. Now I've got all those statistics. So if I'm creating a box chart or I want to compute the spread of values, I'll get all those statistics using a single reducer here. Pro tip is when you are creating your composites, typically you do median composite. If you're working in a very cloudy region, even after applying cloud mask, there might be some cloudy pixels. And imagine you have 10 images that you're trying to create composite from. 7 of them are cloudy. If you do median composite, still you'll get cloud. So in those cases, where you're very cloudy region, do a percentile composite. Instead of saying dot median, you'll say dot reduce, reduce the percentile 25. And you'll get much better results. So that was a script for the combined reducers. We'll now move on to understanding repeated reducers. So now you have one reducer. We saw in the previous section, you can combine it with another reducer. But what if you have multiple inputs and you want to run the same reducers on multiple inputs? So you can repeat a reducer n number of times. Right? So you have 5 inputs and I have one reducer. I'll say repeat it 5 times. For each series, do the same operation. So you take a reducer object and you say dot repeat and will repeat n number of times. Okay. This is done intrinsically in some of the functions. So let's say you have an image with 13 bands and you say reduce region. You'll get 13 different values, one for each band. If you read the documentation, it'll say if you give one reducer with one input and you have multiple inputs, the reducer will be automatically repeated for each band. Okay. So in the previous example, we had selected the NDVI band. But if we had not selected NDVI band, there were 2 bands, EVI and NDVI. We would have got 2 values, NDVI mean and EVI mean. So reducer will automatically repeat for each band. So some functions will automatically repeat the reducer. Some functions won't. Some functions, if you read the documentation, they'll say you need to repeat the reducer for every different input you have. Okay? So for example, this function reduce columns will not repeat. You say, I want to compute stats on 3 columns, and you say reduce the mean, it'll fail. Say, I have 3 inputs, and you have reducer that takes only 1 input. So then you have to say, I'll take 1 reducer, repeat it 3 times. Okay. So make sure when you're using a function that requires a reducer, each function behaves differently. So make sure you read the documentation. Let's visually see what the reducer does. We have this 2 series. Okay. And we want to compute the mean. If I just give my input like this, it'll fail. Let's say I have 1 reducer, 2 input. This doesn't work. Mean takes only 1 input. So you'll say, reduce the mean, repeat 2. And then it'll run on each series and you'll get 2 outputs. Let's see a code example to see how the repeated reducer works. Here we are in the repository with script 2a. This is an example of a repeated reducer. First, I want to show you this data set. This is a really cool data set. I can think of many applications, and whenever I've shown this data to people just always get fascinated. This is a data set by this company Ookla. If you've ever done speed test on your mobile phone to check your internet speed, that's the company. And your location when you do your speed test is logged anonymously, and that goes to the company. The company knows that at that long, this was the internet speed at this time. And they publish this data as an aggregated data as an open data set. So let me just first add this to the map and show you. So this is a global layer. You get this tiles every quarter, and it's available in this GE community catalog. So you can go and find the link to the data. It's already there in Earth Engine. And wherever you live, you'll have a polygon where you'll go and can see what was the internet speed based on the users that measured it there. So if I want to understand the internet speed in the city, I come here and you can see I have a grid. I think it's a 100 meter by 100 meter grid. And I have the pixels, and you can see for within each pixel, if I see this grid, if I inspect, this is the polygon. Within this polygon, I have the average download speed in kbps, average upload speed, and average latency. This is from all the devices that measure. So it says in this quarter, in this grid, there were 39 tests. And this was the average of those tests. Right? You can kind of see so many applications if you want to understand how the internet speed vary across the city. When I was teaching a class in Johannesburg, I just loaded the data, and you could see all the regions which are poor neighborhoods. because there are the low internet speeds. They had 2G speeds, and all the affluent neighborhoods had higher speeds. So again, you can understand the demographics just by the internet access speeds. So you have the upload speed, download speed, and latency in milliseconds. Okay. So let's see how we can compute some stats on this collection. Let me just uncomment this code. So again, I'm selecting a region. This is city of Bangalore in India. I'm just filtered to the geometry, and this is all the tile measurements for this city. So it's a feature collection with multiple polygons. Let me just print the first one to show you what that looks like. So each polygon has these properties. Let's say I want to understand for this city, what is the average download speed on the whole. So that means I want to compute the average download speed for the city. So I want to now compute the mean of all the polygons that are here. So let's see how to do this. We'll say, take this. If you want to compute stats on just one property, we can use this aggregate functions. You can see there are all this aggregate. We have aggregate count, aggregate mean, etc. Right? These are, again, shorthand functions like you have mean, median, like that. So we can just say, give me the aggregate mean of this property average download kbps. And this will compute for all the polygons within the region, the average download speed. And this is the value. And we can just print, let me just get this number. Sorry, this is just number anyway. So we'll just say stats dot divide by 1000. And this will be the speed in megabyte. So the average internet speed in the city of Bangalore is 17 megabytes, 17 Mbps, according to all the tests. Yeah. Now, let's say we want to compute average download as well as upload speed. Yeah, so not only download speed, but average download and upload speed. So we have two properties. We can use this reduce columns function. And say what reducer we want to use. We want to use the reducer mean. Select as which columns we want to run it on. So we'll use the average download and upload both. Weight selector, if you want to give more weight to one column and the other one, you can specify that. Otherwise, this is the one. Yeah, so let's see. Error. Why? Because it says reducer mean got two inputs. It can only work with one input. Why? Because this function doesn't automatically repeat your reducers for you. Let's look at the function. Applies reducer to each element using the given determined inputs. It doesn't repeat by itself, so we need to repeat it using code. So now we say I want mean of all, both the inputs. I'll say repeat this 2 times. So we have 2 inputs, 2 columns, and mean will repeat 2 times, 1 for each column, and you get the output. Okay. Mean of first input, mean of second input, average download speed, average upload speed. And we'll just get the print the values. So and this is a dictionary called mean. So it's we'll extract that dictionary. It's a list. We'll say, get me the first number and the second number divided by 0. This is some post-processing. So now we get the average download speed and upload speed that we computed using a single operation. The answer is the same. It's just that we repeated the reducer for both the inputs together. So repeated reducers, there are functions such as reduce regions. If you look at the documentation, it says either the reducer must have the same number of inputs as the input bands, or it must have a single input and it'll be repeated for each band. That's what I meant to read the documentation. So if you have a 10-band image, you have one reducer, the documentation says it'll repeat it 10 times. Or you can have a 10-band image and give me a 10-input reducer. It should be either of those. That comes to an end of our second script of repeated reducer. The next topic is grouped reducer, arguably one of the more confusing reducers. If you see this in code and you don't understand what's going on, this can get super confusing. So hopefully I'll explain you by visually so you can understand what's going on. This reducer allows you to specify multiple inputs and group the input series by another series. So this is your standard group statistics. When you have, say, two values and say, I want to compute average of the first series, but I want to group it by the values from the second series. So if you use the statistics by category tool in a GIS or computer group statistics in Python or R, this is what the group reducer does. This requires at least two inputs. You can have multiple inputs, but at least two inputs, one or more input specifying the series which you want to compute the statistics on. So you have one band, two band, etc. The statistics will run on those input bands. And you need at max one input to say, group the statistics by the values inside of this. Okay. So one band or one input containing categories and one or more input containing the values that you want to compute the statistics on. The way you create this reducer is you take the reducer and say, I want to compute mean. So you start with E reducer mean and say, but group it by this group field. So you specify out of your input, which series contains groups. Let's say you have 3 inputs. You can say the first 2 are for computing statistics. The third one contains the categories. So you'll say group field 2 will be the third category. Group field 1 means the second series has the groups. So if your first band has your classes, you'll say group field 0. If your second band has the classes, you'll say group field 1. Okay. So that's what the group field means here. Let's see this visually. You have 2 inputs here, and you say E reducer mean, group it by 1, index 1. That means group it by the second input. So you have the value 2, 3, 4, 5, 6. You want to compute average, but not average of everything. You say average by group. So say for each item, look at what is the group of that. You find all the unique values in input 2, and you compute the average of each unique value. So here we have these 3 values, which are 1. So you'll say for all the class 1, this is the average. For class 2, this is the average. Okay. So you will get 2 outputs, one for each class found in your input. Okay. So this is what group statistics does. You specify the inputs and you say group the statistics over the classes contained in some other series. Let's look at the code example for this. Here we are starting with a point geometry. We're just buffering it by 5 kilometers. And we have this region. We have loaded the Sentinel-2 level 2 data. So this is the Sentinel-2 level 2 image. We also have an image of land cover. This is using the ESA world cover image. So we have now classes. So you can see the image is colorized by each class. And we have, say, water here, urban, vegetation, and all of that. And we have some pixel values in the Sentinel-2. Let me inspect one of the pixel values. You'll see that at each pixel, I have some band reflectance values. And I have a class. So this is class 4. This is the reflectance value. If I inspect somewhere else, it'll be another class 7, and these are the reflectance values. I want to know in this region, what is the average reflectance of each band for each class? So in my region, what is the reflectance of water look like? Maybe there are 1,000 water pixels. And all 1,000 have different values, right? Different reflectance values. What is the average reflectance of water in my region? This is called spectral signature. If you want to generate a spectral signature for your features, you have to do this. And let's learn how to do this one. Okay, so we have two images, one with the Sentinel-2 image, one with the land cover image. So if I want to compute some statistics, let's extract some samples. We have our composite image. We'll add the bands of the classified image. So we have this 12 bands of Sentinel-2, one band of the classification. So we created this stacked image. This image would have like literally 100,000 pixels, right? So we can't compute stats on everything. Let's take a random sample. If you have a classified image, you can use this function called stratified sample. And we'll say, give me 20 random points per class. If there are 10 classes in this region, we'll get 10 times 20, 200 points. What we have to specify, what is a class band? And we'll say that classification is the class band. The region is geometry, scale, what scale we want to run. This is the resolution of the data, which is 10 meters. You can specify other options, but we'll just specify tile scale. Now the samplings are quite memory intensive. So if you get a memory error or any error where the input values is too large, specify a higher tile scale. This will allow you to run the computation across more machines, and it will give you the computation will finish faster. There's also this geometries parameter where by default, this will just generate a table of values. So you get 200 points with their spectral sample values. If you want to visualize this on a map, you can say geometry is true. By default, geometry is false, so you don't get the point that long. But if you want it, you can do this. Right now, we don't want it, so I'm going to keep it like this. Let's print the samples and see what it looks like. So we had a stacked image, 13-band image. We sampled it, and 20 points per unique value of this classification band. We got 160 elements. So there are 8 classes, 20 points per class. Okay. Let's see the feature. We have the first feature. This was the value at that pixel, all the reflectance values, classification 0. The second one, different values, classification 0. Okay. So these are all class zeros, but they have different values. And I have 20 such values per class. Now I want to compute what is the average value for each band per class. So I just want 8 values. I don't want 160 values. And this is the case for group statistics. So we'll say compute the average value of band 1 by class. Okay. Let's see how to do this. This is a feature collection. So we can use the reduce columns function. So we'll say take samples and we'll do reduce columns. What reducer we want to use, let's specify a little later on. Selectors, what bands, what columns you want to do. For now, let's just say I want band 5 and classification. Just for simplicity, we're going to do all the bands. First, right now, we just do 2 inputs, band 5 values and classification. I want to compute the average value. So we'll say reducer mean. But not just any mean, I want a group reducer. So I'll say dot group. And we'll say group field. Which is my group field? I have 2 series, series 0 and series 1. My classes are here in series 1. So I'll say group field, series 1. By default, the groups are named as a group, but if you want to change it, you can change it. Right now, we just keep it like this. Let's print the result. So imagine we had 160 inputs, different features. We did a group statistics. We get this dictionary. So there are 8 groups because there are 8 classes. Group 0, mean value of band 5. Group 1, mean value of band 5, and so on. Okay, so we got 8 values, mean value per each group. Okay. So this is how you do group statistics. You specify the input, which is used for computing statistics, and then you say which is the input that is used for grouping your values. So we took 160 individual points. For each point, we just grouped them into 8 classes, and we got the average value of band 5 in each of those classes. If you want to compute for all of the bands, so all 12 bands, I want to compute the statistics. We have to do some, let's write some code. We'll just say, give me the list of bands. So composite.bandNames is a function to get the list of all the bands in an image. We add this classification band, and we say, these are the total number of bands we have. And then we want to compute what is the index of the classification band. Again, we don't want to hard code this value. If our composite has 13 bands and we add classification, that'll be the 14th band. So we just use this function index of the property. So from a list, we say, what is the index of this thing? So let's just print this group index. And this will tell us what was the index of the classification band. So that's what we use for grouping. Yeah, so this is the 12th index, is the index of a group band. Now let's do our statistics. So we'll say, I have my samples and I want to do reduce columns. I want to compute my selectors will be my band names. So this will be all our properties, right? So all the band values plus classification, that's our selectors. My reducer, I want reducer mean, but this mean has to be how many times? 12 times, right? I have 12 inputs. I don't have just one column that I want to compute. I want to compute statistics of 12 columns. So I'll say, take the mean reducer, repeat it 12 times, and then group it by the 13th value. So I have now, let's say, group it. So we have this value num bands, which is the number of bands. And then we'll say group it by the group index. Let's print the result. So we have 160 samples, each sample having 13 values, 12 reflectance values, 1 group value. We now group them into 8 groups because 1 group per class. Each group contains 12 values, 1 for each band. So now we say in group 0, class 0, this is the average value of all bands. And this was computed by the repeated mean reducer grouped by the value for the class. One problem that you'll see when you do group reductions is the output is quite nested. You get a dictionary with one key called groups. That's a list of another dictionaries where the key is the name ID of the group and the value is a list of another values. So again, to turn this into something that you can export or use later on, we need to do some post-processing. And the post-processing code will be very similar. All your group statistics post-processing will look something like this. So first, let's just extract the groups. So first step, we have the stats, which has got one key called groups. Let's just extract that. So I will say stats.get groups, and you get a list. So once you get this group key, that will be the list of all the 8 statistics. So we have a list of dictionaries. So if you want to further process, we'll say group stats is a list, we'll map a function. And each function will get an item. And for each item, we'll extract, each item is a dictionary, right? So we'll extract the values and the keys and the values. So we'll say each item is a dictionary, get the mean value, which is this, get the group value, which is this group 0. Now this mean has all the different values. And now you can take this data and turn this into a feature where, say, take all the values. We have the properties. We know what are the band names, create a dictionary. The first one is B1, second one is B2, and so on. So we create a dictionary and return a feature, e.feature, where we return all these values with the proper keys, the band names, along with the class value. And this whole thing will return a list of features. So we'll just store them as FC and we'll convert them into a feature collection. Again, this one is just post-processing your group reduce output into a feature collection. So if you see now, we'll have 8 features, one for each class with the keys and class name for each of those values. So we have 8 features, each feature having property saying that this is the average reflectance of band 1, band 2, and so on. And this is the class. We just took the class 0. We had a dictionary here, which had the class names. So we knew the class names. So we'll say class 0 is tree cover, class 2 is grass land, and so on. And we just converted this. So this is now a nice table. If we export this as a CSV, we'll get a nice table with the average reflectance of each class for each band within this region. Okay. Next is a topic on weighted versus unweighted reducers. If you ever migrated your workflow from a desktop-based system, ArcGIS, QGIS, GeoPandas, to Earth Engine, you would have run into this issue. The user forum is littered with questions on saying, I did this analysis in Earth Engine, my answer doesn't match what I get in ArcGIS. My area in ArcGIS is different than what I get in Earth Engine. Or Earth Engine says, value is X, QGIS is Y. The reason is weighted versus unweighted reducers. We'll start with this simple question. We have an image, each pixel is value 1. We have this 4 pixel by 4 pixel image. We have a geometry defined by this red polygon. What is the average value of pixels within this polygon? Depending on which software you're using and your thought process on what you consider a pixel, you might get value as 9. Well, I have 9 pixels within my polygon, so I get the sum of pixels is 9. Or you might say, each pixel is not fully covered. It's only partially covered. I'll only consider the partial value of the pixel. So if my pixel is 50% covered, that contribution of the pixel is just 0.5, not 1. And I'll get answer like 5.95. Now, both of this can be right. All desktop GIS and Python or R code will use the first option. They will consider whole pixels, even though your geometry intersects only the partial pixel. There's no way to represent partial pixels in those software representations. So if you consider some statistics and say I computed the sum of values or the average of values, you'll get the first answer. Earth Engine uses weighted reducers. It says if the geometry intersects only half the pixel, I'll consider half the pixels. This is not too relevant if you're working with the high resolution data. So you have 10 meter data or 1 meter pixel size. This difference will be very small. But if, let's say some climate data or precipitation data, and now you try to compute stats where the pixels are very big, you'll run into serious discrepancies between the software. So let's understand how Earth Engine deals with it. In Earth Engine, most reducers use weighted reducers. So each weighted reducer will say, I will consider only the portion of the pixel that is covered by the geometry. So if you take any reducer sum, mean, median, they are weighted reducers. That means if the pixel is at least has some portion of the pixel within the geometry, it'll consider that pixel. There's this 0.5% where you have, let's say you have a very big pixel, 100 kilometer by 100 kilometer pixel, and you have a tiny polygon, which is very small. Earth Engine will say the average value is 0, null. So there's no pixel inside because the pixel is, your geometry is so small, it doesn't even cover 0.5% of the pixel. But for most analysis, your pixel, if it covers more than 0.5%, it'll cover whatever percent it covers, there'll be the contribution of the pixel. That's the weighted value. Unweighted reducers will count the whole pixel, regardless of how much it uncovers, if their centroid is within the geometry. There are reducers such as e-reducer count, which is an unweighted reducer. So give me the count of pixels, Earth Engine will say 9 pixels. Because if the centroid is within that geometry, it'll consider that this pixel belongs to this geometry. Okay, so that's the difference between the weighted versus unweighted reducers. You are able to run any weighted reducer in an unweighted board. So you say, I've computed some mean or sum, but I want to match my answer with what I got in ArcGIS. So you can call .unweighted on any reducer, you'll get an unweighted version of that reducer. So you can say e-reducer.sum.unweighted. which will get you the unweighted value of that. We're now in the script 4A. This is an example of the weighted versus unweighted reducer. Here we are using a test image, which I generated because it's hard to demonstrate this unless you exactly know the dimension of pixels and the pixel values. So I generated a kind of a dummy image. This is my image. This is a 4 pixel by 4 pixel image. Each pixel is 1,000 meters, so 1 kilometer by 1 kilometer pixel. And this is the kind of the polygon of each pixel. And now I have this geometry. Okay, so each pixel values is 1. I have this geometry, which is the red color polygon. Let's compute the statistics of this region, and we'll understand how different reducers treat it differently. So we'll take our image and we'll say reduce region user sum. I want the sum of all the pixels within this red polygon. The red polygon is stored in this variable geometry. Scale is 1,000. And the band name is B1. So I'll just get a value, the key B1. So it says 5.95 because by default, this is a weighted reducer. And our polygon, red polygon, doesn't cover all this 9 pixels fully. So we'll consider the contribution of each pixel of how much overlap it has with the polygon. So this is what you'll get default. If your colleague has run the same computation in ArcGIS, they'll say, my answer is 9, your answer is 5.95, you are wrong. And you can just say, not wrong, I just ran my computation differently. And if you want to prove that you're not wrong, you can say .unweighted, and this will run in an unweighted mode, and you'll get the answer that matches other software. Whenever I'm working on projects, I always use unweighted reducer, so other people can verify my result. Once they're able to verify and say, okay, your computation is correct, then I can say, do you want a more correct answer? And now we switch to a weighted reducer, and that's the more correct answer. Okay? So that's the difference between weighted and unweighted. This can bite you in so many ways. 2 things you should always remember is if your pixel size are very big and your geometries are too small, you might get unexpected result. In that case, let's say you have a 10 kilometer by 10 kilometer pixel and you have very small geometries. And you're running this with a scale 10 kilometer, right? And you'll sometimes get null values. That's one case where you may want to run it at higher resolution. So you'll say my scale is 100. Even though my pixel size are 10 kilometer, you run it at a lower scale so that that small geometry has some pixel value within it. Okay. Also, weighted reducers are more appropriate, but again, if you want trying to match your answer with another system, make sure to run it in unweighted mode and then switch to weighted mode when you're confident about your results. Now that you understand what are the different types of reducers, combined reducers, repeated reducers, group reducers, weighted reducers, unweighted reducers, let's do some calculation. One of the calculation that is often complex for beginners is this computation of zonal statistics. So you have an image, you have multiple zones, and you want to compute statistics of an image from each zone. Zones can be both polygon or rasters. So let's say you have a shapefile of polygons and you want to compute the average value of image for each polygon. That's a zonal statistics. Or you have some raster values with classes and you want to compute some average value. There's also zonal statistics. Some examples of zonal stats, you want to compute area, say flooded area for each district in a state. There are 100 districts. I want to compute the area for each of those. Instead of trying to do one at a time, you can just run zonal statistics and you'll be able to run any reducer for each zone. Average elevation of each seismic zone in a region. You have elevation raster, you want to compute average elevation for each polygon, you can do this. Average mean NDVI for each crop in a classified image. You have a crop classification and you want to compute average NDVI for different crops. You can run any reducer in this mode. So you can say I have some intensity values, and for each zone, each polygon, I want to know the distribution. So you can actually run histogram for each polygon and understand that, right? So again, this is a lot of computation. Instead of doing one at a time, you can just run it all together using the zonal statistics. Let's learn about how to do this in the vector side first, and then we'll compute the zonal stats using the raster data. We have a feature collection with some polygons for zones, and we use this function reduce regions. Reduce region allows you to compute stats from image in a geometry. Reduce regions allow you to specify a feature collection, and you will get stats of an image within each polygon. And the output will be the same feature collection with a new property for that was generated by the reducer. So if you say, give me the mean value, you will get one extra property in your feature collection, which will be the mean. If you have a combined reducer, you'll get, and which generates, say, 3 outputs, you'll get 3 new properties. Let's see an example of this. Okay, so we are now working on script 5A, zonal statistics for vector. I'll show you a new data set. This is a feature collection called ecoregions, quite widely used. This defines polygons for each ecological region of the world. So you can see this is some ecoregion. Each polygon specifies an ecosystem of the similar characteristics. So we have ecoregion polygons for the whole world. There are 846 ecoregions in this particular file. So we have 846 polygons. Each ecoregion is part of one of the 14 biomes. So if I inspect ecoregion, so if I inspect this polygon, this is the ecoregion, and it is part of the biome called deserts. Okay. So ecoregions are grouped into different biomes. Different biomes are grouped into something called realms. And realms are the regions, Asia Pacific and Australia and so on. So we have 846 polygons, and we have grouped them into different things. Let's work with one realm. So we have selected this one realm, and these are all the ecoregions in this realm. So each ecoregion has the property of the name of the ecoregion along with the name of the biome that they're part of. Along with that, we have one raster from this dataset called WorldClim. This is a historic climatology dataset where we have average values of different climatic variables. We are using the Bio01 band, which is the average temperature of each pixel between these years. So take all the historic climate data, and you get one image where the value of the pixel is the average temperature at the pixel, average from 1960 to 1990. There's a V2 of this version, which is 1970 to 2000, and so on. Yeah. So now what we want to do is we want to understand this different ecosystems, and for each polygon, we want to compute what is the average temperature within each ecoregion. Okay, that's a useful thing to compute. We want to understand the climate in each different ecoregion. So we have polygons, we have an image. Let's compute the zonal statistics. So we have zones and an image. Let's compute the zonal statistics. So we take our image, which is our temperature image, and we run our zonal stats function, which is the reduce regions. Plural, autofill, control space to autofill, collection. What collection we want to reduce, we'll just say filtered. So the filtered one contains only the ecoregions for this particular realm. Reducer, average temperature, scale of this. So you'll always need to compute the scale of this data set. An easy way to compute scale is you take the image and you say dot projection dot nominal scale. This is a function that will tell you what is the resolution of that image. Okay, so we just compute that, and we use that for our scale. And that's it. So this will compute the average temperature value from this image at all of those polygons. Let's print the stats. The output of reduced regions is always a feature collection. You input 100 features, you'll get 100 features out. Each feature will have one more property that is generated by the reducer. Let's look at this. So you can see this one had all this input properties, but we have one more property called mean, which is the average temperature value for that particular polygon. And we have those values for every polygon in this collection. So this is how we did the zonal stats. And it's quite simple. Reduce region will give you the zonal stats. Now we have this feature collection. This one has one polygon for each ecoregion, and we have many different biomes within that. What is the average temperature per biome? So now we want to say, I have this mean value. Can we get the average of all the averages, but grouped by each biome? Right? So instead of computing separate temperature, we want to now group the statistics by each biome. And that's your group statistics. So if we want to now take this one step further, we'll say I want zonal group stats. So I'm just going to rename this variable to be zonal stats. And now we want to take the zonal stats, and since this is a feature collection, we can run reduce columns on that. And now we can say, give me the 2 columns. So mean temperature and biome. So we have, I'm going to just set this. So again, I don't want the key to be mean. I want it to be mean temp. So I can use the set output function to change this. I can have this 2 columns. I want the mean temperature and biome, and I want to now group it by the biome. So my reducer will be e-reducer mean, and again, output will be mean temperature. Group it by the group field 1. So group it by biome, and the default group name will be group. I'm going to rename my group name to be biome. So now we get 10 outputs because there are 10 different biomes in this particular region. Biome 1, mean temperature. Biome 2, mean temperature, and so on. So at first level, for each polygon, we computed stats. Then we aggregated it for statistics by each biome within that. And again, this is your output of a group statistic. So we need to post-process it. So let's just copy paste the code. Very similar to the previous script where we just take this list of dictionaries, post-process this into a feature collection. Now you get this output that you have a feature collection, and each feature is the biome and the mean temperature. Finally, when you're doing this kind of group statistics, your results will often time out because it's a long computation. So you can always export the result. So here is some code. We're just exporting this both the tables. One is the mean temperature by ecoregion, which is the first output, and then mean temperature by biome. We can export both of them as a CSV file. And I want to show you once these exports are run, what the output looks like. So this was the first output. So we had our polygons and an image. We said for each polygon, give me the average value. And now we get the biome, ecoregion, and the temperature. And you can see this has a lot of values. Now, in the next step, we say for each biome, take all the ecoregions and compute their average. So in the next one, we get for each biome, the average temperature. Let's learn about raster zonal statistics. Raster zonal statistics are something that is very powerful, but it's out of reach for many beginners. Now with this session today, you understood the nitty-gritty of reducers, how to use group reducers, combined reducers. You're now able to attempt to understand how this works. And once you understand it, it'll solve a lot of your problems. Since Earth Engine scales really beautifully for images, if you work in the image space, you will get much better result. Many times where people say, I have different classes, I want to compute average value per class. And they will say, I want to vectorize this and compute polygons and then compute stats. In Earth Engine, that's a very inefficient operation. If you have rasters, work with rasters. So you can compute zonal statistics for rasters by saying, I have one band of pixel values, one band of zones, compute statistics of the first band by the second band. And that sounds like a group reducer we just learned earlier, right? So group statistics, group reducer on rasters will give you raster zonal statistics. Okay, it's the same thing that we did earlier, but now you can think of that operation as a zonal statistics where you can compute the value for each zone, each class, and you can arrive at the statistics of different pixel values. Let's see an example. In this example, I want to show you a few new things. One is how unsupervised classification works in Earth Engine. So the idea for this is we have a really nice algorithm called water detect. This is one of the best algorithms I've come across, which is an automated algorithm for detecting water using machine learning. When you say automated, that means you don't have to give any human input. If you're talking about supervised classification, that means you need to generate training data. This algorithm works completely unsupervised, but it uses some innovative way to turn this unsupervised algorithm into which runs without human input. So the way this algorithm works is first we're going to do unsupervised classification on an image. We are starting with a Sentinel-2 image. So we take a region, we take our Sentinel-2 image, we mask clouds, we create a composite. We also compute some indices. Since we want to detect water, we'll compute some water indices. So we have NDWI, MNDWI, and the SWR2 band, which is the band 12. So we have these 3 bands, and we're going to take these 3 bands as our input features for doing unsupervised classification. So 3 bands, and we want to say find groups of pixels which look similar in those 3 bands. And those will be the different groups. We take some training data, which is we take our 3-band image where we take the NDWI, MNDWI, and the band 12. We stack them together, we sample some points, and we get each point where we have value of NDWI, MNDWI, and band 12 at that pixel. So that's our training data. And this features, we have 1,000 such points that we have sampled from this image. Those 1,000 points goes into an unsupervised clustering algorithm. And it'll go and find the pixels that look similar and it'll group them together and output with clusters. So we are using this algorithm, cascade k-means. We'll say, give me anywhere between 2 to 10 clusters. And we train it with this data and we get our clusters. So each of our training features looks like this. We have 1,000 points and we have the sampled pixel values from this. There's no class. We're not defined what each pixel's class is. We just gave this pixel values. The cluster went and say, I detect n clusters. So when we give this input data, the cluster will come out and say, I've detected maybe 5 clusters here. I don't know which cluster is what, but I just say these are the pixels which have similar values. And we have visualized this. There's this function called random visualizer. You give an image with unique pixel values, it will apply a different color to each pixel. So all the pixels in yellow are similar, all pixels in green are similar, and so on. And if I overlay this on your Sentinel-2 image, you can see it is kind of matching my image quite well. But this is being an unsupervised algorithm. I don't know what is what. Right? I don't know what is this pink color. I don't know what is this green color. In a typical unsupervised workflow, you'll now come in as an analyst and say, oh, this looks like water. So cluster 5 will be water. So you can see if I click here, this will be cluster 2. Right? So the cluster 2 is water. And then I'll go and tag those. Cluster 2 is water, cluster 1 is vegetation, and so on. Right? But I want to now do this completely automated way. So I have clusters. We can apply one statistics. We say we have the NDWI values here. Let's find the average NDWI value for each cluster. Cluster 1, all pixels belonging to cluster 1, compute their average NDWI value. Cluster 2 NDWI, cluster 3 NDWI. And the cluster, which is water, will have the highest NDWI, right? Because water has high NDWI. So if I have 10 clusters, I'll compute average NDWI in each of those clusters, and I'll pick the cluster having the largest NDWI value, and that'll be my water. That means I don't need to manually tag it. I'll run it on any image. It'll create clusters and it'll pick the cluster with the highest NDWI as being water. Okay, let's see how we can implement this. So we'll compute stats. We have our image. We have our NDWI image, which is a water image. We want to compute average NDWI value for each cluster. So we'll add the bands of the clustered image. We have a stacked image, 2-band image, NDWI, and clusters. Let's run reduce region. We'll apply the reducer mean, but not just any mean. This will give me the average value of NDWI in the whole region. I want to group it by the second band, which is my clusters. And I'll just name them as clusters and run this whole operation on my geometry at 10-meter scale. Since my goal is to compute this automatically in real time, we can compute the stats at a lower resolution. We'll not get fully accurate stats, but all we are interested in is just the cluster with the highest NDWI. So it's okay to run this at a lower resolution because we can now get the value at the, we're just interested in approximate value to find the water cluster. We get 6 values because there were 6 clusters in this image. Again, these clusters are determined automatically by the clustering algorithm. And now we have the value. If you just inspect this, you can know which is the cluster with water, right? One with the highest NDWI value. So cluster 2 is water because other clusters have very low NDWI. This is the one having the highest NDWI, but we want to pick this automatically. So how can we just say, pick the cluster having the highest NDWI? Let's do some group post-processing. So we'll create a list of 2 values, and I'll explain why the list is important here. So same output from a stats, we'll just go from this nested list to a list of 6 values. So we have list of lists, NDWI cluster, NDWI cluster. Now we want to automatically pick which is the cluster number for the one having the highest NDWI values. So again, we have this value. Can we do this automatically? And this is where another kind of reducer comes into play. Let me just explain. So let's say I have this list of lists. I want to know which is the highest value from this list and what is the name of this. So this will be the value, and this is the, say, the identification of the value. So I want to pick this value because that's the highest value, but I want to know what is this value, the second value. So I can run a reducer. Reducer max has this parameter called num inputs. There are only 2 reducers having this parameter, num inputs. There's one more Kendall's correlation. Let's see what this is. So you can say, give me the max value out of this, and you have 1 input, it'll give you the max value. But if you have 2 inputs, this function says, if you have 2 values, it'll tell you the maximum value and the corresponding second value where the value was the highest. So if I run this with, say, reducer max 2, you get 2 values. That maximum was 10, but the corresponding value was B. So now we say, I got the maximum value from a list of lists, and I know what was the corresponding value here. Now we can know how we can find this, right? We can say, pick the value from this list of lists where the NDWI is highest and give me the number of the cluster corresponding to it. So I'll take my group stats list and say reduce with max 2, and my water cluster will be the cluster with the key max 1. So whatever the NDWI, I don't care about the max NDWI. I only care about the water cluster. So now I got my water cluster, and I know what is water. So we went from a Sentinel-2 image, sampled the values, trained a cluster, it detected 6 clusters. We found the NDWI value for all clusters, found the cluster having the highest NDWI, identified those clusters. We can now select all pixels belonging to that cluster. And that's our water. Okay. So now we went from a Sentinel image to water with no supervision. So now you'll see that we have this image, and you'll get the value of the water cluster automatically determined from this. You can see this is detected all the water pixels. If you ever done supervised classification, you will know that your result will not be this clean, right? You'll get a lot of this outliers and noise, etc. This is a very clean output, completely automated. This is one of the best algorithms I've found for automatically detecting water pixels. It's quite reliable, quite robust. And again, you don't have to have a supervised method. You can rely on this group statistics and apply that to find the cluster with the highest water. All right, so I want to conclude this session by showing you the course page. All the code that I showed today, along with the documentation and the presentation, is available on this page on our OpenCourseWare site. You can access this. We'll keep adding more material here as the time progresses, so you can come back and check for more materials.